A very good afternoon to one and all. Hope I am audible. I, Dr. Geetanjali, Department of Physics, take this opportunity to welcome you all on behalf of the Department of Physics, Bangalore Institute of Technology, to a webinar on Photoelectric Effect 100 years. Photoelectric effect was fundamentally significant in the development of modern physics because of the puzzling questions it raised about the nature of light, that is, particle or wave nature. It was then finally resolved by Albert Einstein in 1905, for which he was awarded with the Nobel Prize in 1921, exactly 100 years ago. This phenomenon remains important even today for research areas like electronics, material science, astrophysics, etc. In fact, it is the basis for a variety of useful devices. Department of Physics, DIT, known for its self-motivated outlook and always stands in the forefront in organizing important events like this. In continuation of our department tradition, we have decided to celebrate the 100th year of this accomplishment by arranging a webinar. We believe basic science is the foundation for engineering. Keeping this in mind, we have been organizing many events like this, and it will certainly go on. So, dear all, I now request Dr. G.K. Nasimamurthy, convener of this webinar, Department of Physics, to deliver a formal welcome speech. Over to you, sir.
Good afternoon, one and all. Present in this webinar, we are proud to acknowledge our principal, Dr. Ashwath MU, plays a pivotal role in supporting in conduction of webinar. Today, we are conducting a webinar on photoelectric effect and its applications. I would like to welcome the administrator of Rajyavakalgara Sangha, Sri Karigowda, and the CEO, Sri Siddaramaya, on behalf of the Department of Physics and myself. I am also honored to extend the welcome to our beloved principal on behalf of Department of Physics and myself. We, the Faculty of Physics Department, extends warm welcome to the two speakers of today's webinar, Dr. Sp Basuraju and Dr. HSS Ramakrishna Matte. Dr. SPB, well known to students and fraternity as a writer of engineering physics book, today he will enlighten us with the history of photoelectric effect. Dr. HSS Ramakrishna Matte is a young and eminent scientist in the Center of Nano and Soft Matter Sciences. He will be illuminating us with an overview of new generation of solar cells. Once again, I would like to welcome the two speakers of today's webinar. I also welcome my department colleagues and the staff members of BIT. Last but not the least, I would like to welcome all the participants of this webinar on behalf of the Department of Physics and myself. We will now commence the webinar on photoelectric effect. Thank you.
On behalf of the Department of Physics, I welcome Dr. G.K. Nasimamurthy to the webinar. I now request our HOD, Dr. D. Nagaraja, to give an insight about the webinar. Over to you, sir.
Good afternoon. Good afternoon. I am Dr. Nagaraj, Professor and Head of Department Physics. I am here to give you a brief introduction to this webinar. In 1887, when German physicist Hertz did some experiment in connection with radio waves, he never thought that this discovery is going to open a gateway to a new world of physics. Being a strong supporter of wave theory of light, Hertz wanted to confirm it through a photoelectric effect experiment. In fact, it is one of the ironies of history that same work, that is photoelectric effect, to demonstrate that light is a wave, also gave the first hint for particle nature of light. Okay, when you think of Albert Einstein, what do you think of? General theory of relativity, black holes, E equals mc square, or crazy hairs? While he certainly made significant contributions to all of those topics during his lifetime, Einstein was perhaps even better known in his time for his work to understand this photoelectric effect. In fact, when he was awarded the Nobel Prize in 1921, the honor was stated to be for his service to theoretical physics and especially for his discovery of the law of photoelectric effect. This discovery is so important and Nobel Prize worthy because Einstein suggested for the first time that light is both wave and particle. This phenomena, known as wave-particle duality of light, is fundamental to all of quantum mechanics and has influenced the development of electron microscope, photoelectric cells, photoconducting cells, photomultiplier tubes, light detectors, sensors for pollution monitoring, solar cells, and many more. In fact, photoelectric effect is not only responsible for Einstein getting Nobel Prize in 1921, we can also see its role indirectly in Planck's Nobel Prize in 1918. See, Planck proposed quantum theory in 1900, but only after 18 years he got the Nobel Prize. And Compton, who explained Compton effect in 1922, awarded with Nobel Prize in 1927. In both these Nobel Prizes, you can see the indirect role of photoelectric effect. In this connection, we at DIT thought of celebrating 100th year of major accomplishment in a more meaningful way by arranging two talks, one on the history of photoelectric effect and the other on the application part of it. So this is the background of this webinar. Hope our speakers will certainly illuminate you on both these topics and hope you all will get benefit and enjoy by this webinar. Thank you.
Thank you very much, sir, for highlighting the importance of photoelectric effect. Now is the time to listen to today's first talk, which is on history of photoelectric effect. That is going to be given by Dr. Sp Basuraju, formerly Professor and HOD, Department of Physics, BIT, Bangalore. I request participants to post their queries, if any, in the chat box, so they will be answered at the end of both the talks. I now invite Ms. Ashita R., Assistant Professor, Department of Physics, to introduce today's speaker. Thank you.
Good afternoon, all. I'm Hashita. I'm happy to introduce first speaker of this webinar. Dr. Sp Basuraju obtained his MSc degree from Mysore University and PhD degree from Bangalore University. He served at Bangalore Institute of Technology from the time it started as its HOD of Physics for 28 years before retiring as professor. He has written books on engineering physics and theory for the student of VTU. He is also a YouTuber and has put up short demonstration on 8 physics experiments, and another one on history of Newton's rings as a part of an elaborated talks on history of microscope in the web. He is passionately interested in the historical developments of scientific topics and biography of scientists. He has been invited by various institutions and universities to speak on topics such as the history of black body radiation, early history of quantum mechanics, history of laser, and biography of Sir C.V. Raman. He is also interested to speak on history of electrodynamics and history of life and achievements of Madame Curie. I welcome you, sir. Please take over the session, sir. Thank you.
Good afternoon, all the viewers. Thank you, Ma'am Harshita, for introducing me to the audience. Before I start, let me express my gratitude to Dr. M.U. Ashwath, Principal of BIT, Professor D. Nagaraj, the HOD of Physics, Dr. G.K. Narasimhamurthy, the convener for this program, and the physics staff of BIT, the organizers for this program. Now, the listeners. I'm thankful to you all for having been here to listen to my talk. I am really excited to be here in my institution addressing you all. My talk is, as you guess, going to be the history of the photoelectric effect. I am interested to tell you about what all happened before photoelectric effect was discovered, and what all happened in its progress, and how the Nobel Prize committee decided to give him the Nobel Prize, and later on how Einstein withstood all the opposition by the great stalwarts. Now my story starts from the discovery of electromagnetic waves by Maxwell in the year 1964. The story starts from the year 1964 when Maxwell proposed his work on, he did his work on electromagnetic theory of light, but there were no takers. There was nobody who was able to catch Maxwell and continue his work, because the mathematics involved was a bit deeper, and it was not known to many people regarding his use of vector notations and other things. So it went to the cold storage. But yet there was one person in Germany who was interested. Those who wanted to learn about Maxwell's equation used to go to Germany to listen to the most popular scientist of his time in Germany, that is Helmholtz. Helmholtz was the person who handled Maxwell's theory in his classes, and he wanted to prove the existence of electromagnetic waves. So he had a brilliant student by name Heinrich Hertz. He in turn inspired Heinrich Hertz, his brilliant student, to take up the investigation. So after 1864, we are in 1886 when Heinrich Hertz started his experiment. He started his experiment by conducting some kind of discharge, conducting experiment on the discharge of electricity through metal spheres. The arrangement looks like this. Here you can see here you will go to see the actual setup used by Hertz, wherein you will see two metal spheres which are separated by a small distance. The big spheres there are something like charge storage devices, and when the setup was switched on, they used to discharge. The setup used to discharge the electricity across the two spheres. This is the actual setup. See, the discharge used to take place here. Show this. Okay, that was show this. See, the discharge used to take place between the two spheres, and that what you were seeing in the table, that between the two big spheres, there are two small spheres at the center. And that day, one day in the year 1887, when Hertz was about to start the experiment, it so happened on the table behind him, there was one more metallic loop which had two spheres of identical shape and size and separated by the same distance of having the same distance of separation. So when Hertz switched on the apparatus, when discharge started, the sparks he was observing, but he heard some kind of crackling sound behind him. When he turned around to see what it was, then he saw sparking taking place between the two spheres which are attached to the loop. Then suddenly the thought flashed across his mind that the electromagnetic waves which are produced by the discharge here in the main loop, that has gone out, and then those waves have been caught by the other loop behind him, and that is how the sparking was taking place between the two spheres in the next loop. So the one which was acting like a transmitter, and behind him it was acting like a receiver. The schematic is like this. Then what happened? Hertz is successful now. He has got the electromagnetic waves produced on his table. Then out of curiosity, he took a glass sheet and then put it in between the receiver and the transmitter. He just inserted and then he saw the sparking intensity reduced in the receiver. He got a bit, surprised how this is acting. So then what he did was he cleaned up the glass plate and made it very clean and then inserted between the receiver and transmitter. Then also there was a reduction in the intensity of the discharge. Then he thought, what's happening over there? The light that has been produced during the discharge in the main, that is the transmitter, is now passing through the glass sheet, of course, without interruption, but the glass doesn't transmit ultraviolet light. Then he came to the conclusion that the discharge that is taking place in the loop, in the receiver loop, is influenced by the ultraviolet rays emitted by the transmitter. That's how the first instance about ultraviolet rays causing emission of electrons came to the knowledge of the people who conducted the experiment. But now the problem was this. During those days, I'm talking about the year 1887, at that time, there was no knowledge about how the electric current is flowing in the circuit and about the electrons. Electrons hadn't been discovered by Thomson. See, the idea was the electric current in the circuit is due to the flow of negatively charged fluid, something like a liquid. Negatively charged liquid is flowing in the circuit. That's how the current is passing. That's how the people thought. There was no knowledge about the electrons. So there was no basis for Hertz to think about what's happening there. He was not able to understand what has the ultraviolet rays got to do with the discharge taking place in the receiver loop. So he thought the case to be a hopeless case and dropped it. But he reported the matter to a journal and then he did not pursue the matter afterwards. That was in the year 1887. But the following year, another German physicist by name Wilhelm Hallwachs knew something what Hertz was not knowing. Well, what is that he was knowing was this. In the year 1883, some 3 years before, Thomas Alva Edison was conducting some experiment. He had a problem. He was facing a problem regarding the blackening of the electric bulb he had invented. The portion which was in front of the filament used to get blackened. He was wondering what's happening over there because it's all vacuum surrounding the filament and there was no connection, electrical connection between the surface and the filament, but yet it used to get blackened. After conducting some experiment, he came to the conclusion that the negative current is reaching from the filament to the body of the bulb by means of certain kind of particles. So negative particles, he was not knowing about electrons, but he chose to say that there are negative particles which are emitted during the heating process of the filament. So that's how Hallwachs got the idea that the same might be happening in the case of Hertz experiment also. Then he thought that the ultraviolet rays must be making the negatively charged particles to get emitted from the metal surface when the ultraviolet rays fall upon the spheres. That's how Hallwachs supposed it, but yet there was no proper theory. Hallwachs made the prediction, but it was not a concrete one. So the things remained like that from 1887 to 1897, 10 years passed. In the year 1897, J.J. Thomson discovered electron. The discovery of electron electrified. It revolutionized all the electrical phenomena, both in physics and electrical engineering. The things started, changing in the view of the people who are working in the two fields. Then in the next year, that is in the year 1898, Thomson himself made the comment that during the photoelectric effect, electrons are emitted. No doubt the negative charges are being emitted, but what were the charges? They are electrons. That's what J.J. Thomson told. So from 98 1898 to 1900, there was not of any improvement. But in the year 1900, something happened. In the year 1900, two more additions were there to the subject of physics. Those were Paul Druday's free electron theory and Planck's idea of quantization, Planck's idea of quantas. Let's see this Paul Druday's idea of free electron theory. What Paul Druday told was, say in the metal, there are two status for the electrons. One is the bound status, other one is the free status. Those electrons which are in the bound status, they are like family. They won't leave the parent atom, they won't drift. Whereas these other electrons which are free, they are like vagabonds. They keep moving around in the body of the metal, like how the gas particles move inside a vessel. So Paul Drude did not tell anything about this photoelectric effect, but Paul Drude's free electrons were the ones which could become the photoelectrons later on whenever there is photoelectric emission. So that's how the free electrons theory was made use of in explaining the photoelectric emission, photoelectric effect. Now coming to the Planck's theory. See, we all know that Planck gave a theory on the black body radiation emission, the black body radiation. What happened was, Wheel's law had failed, but that came to the notice of Planck. He made certain kind of adjustments with the Wheel's law and rigged up one equation. The rigged up equation worked very well, and the equation fitted very well with the experimental curve. So that's how his equation was successful. But Planck, when he decoded the equation's meaning, then he came to know that it represented something very unusual. You see, the black body, when it was heated, it used to give the electromagnetic waves. All right, but it was not giving like globules. As per the equation that he had worked, when he made the interpretation on the basis of the physics analysis, then he found that the energy is not radiated in terms of electromagnetic waves, but they were emitted in small packets. They were like maybe electromagnetic waves, but the energy itself is coming out as small packages. So those, he was not able to understand why not electromagnetic waves, why it is getting split into small units. He was not able to understand. Then he thought maybe his theory was not really all right, but for the time being, his equation is is fitting into the experimental curve, that's all. Yet, if this is truly happening, then the black body must be emitting small units of electromagnetic waves in terms of quantas. Quanta means actually in German, how much? It is a question actually. How much energy is there? That is the question. So these quantums are being emitted from the black body when it was heated. These used to spread around, like they are spread out of the black body. And what Planck thought was, this is peculiar to only the black body, and it is not happening anywhere else. So his idea of quantization or quantas, he thought it's only peculiarity of only the black body, and then he kept quiet. Now, what is the fate of H? He stands constant. There were no takers. Planck himself was not so much sure about it. He rigged up the equation. As per the equation, when it was interpreted, it gave out the idea that the energy is emitted in terms of small units, and those he named them as quantas, and he further told that the energy of the quantas is E equal to h nu. So that's what he told. That's how Planck gave the theory, and he did not, because he was not having the confidence, he did not pursue it. So H went to cold storage. It started sleeping inside the black body. But it went into a deep slumber for 4 more years. 4 more years it did not come out. But that was not the case of photoelectric emission. Off and down, people used to visit the problem. In the year 1902, the person who took up the problem was third student Philip Leonard. Philip Leonard was an ace experimental physicist. He was the future Nobel Prize winner. He had in his control, in his apparatus, a facility to vary the intensity of the light incident upon the photosensitive surface. He could control the variation of intensity of light by a factor of not 10 times, not 100 times, by a factor of 1,000 times. He made 3 observations. Okay. He made 3 observations. Leonard made 3 very important observations in the year 1902. Number 1, the velocity of photoelectrons is not affected by the intensity of incident light. Brighter light was not imparting more velocity to the, more energy to the electrons. Only the electrons used to come out with the same velocity. There was no improvement in the velocity. It means, what has happened to the bright light that is shining, brighter and brighter light? The bright light, that did not go waste. The brighter light was able to push out more number of electrons. So, but the velocity of all the electrons used to be same, but more number of electrons used to come out with a brighter light. That was the effect of using brighter light. Then what is that one has to do to get electrons with a higher velocity? For that also, Leonard had made an observation that an incident light of higher frequency, shorter wavelength, produces emission of electrons with higher velocity. So that way, these were the 3 observations that Leonard was able to put out from his studies. So this gave some amount of knowledge for the people, theoretical people, to explain why it is happening. But nobody did it. It was in the year 1902, Leonard gave the these 3 ideas, these 3 informations, but nothing happened afterwards. The person who was able to do this was there in Switzerland in a patent office. He was not a noted physicist. We all know that it was Einstein. In the year 1905, Einstein took the problem and then proposed his theory of light, theory of photoelectric effect. For the first time, H was found outside the black body. Somebody was able to use the idea of Max Planck in some other case. So that was Einstein. Einstein told like this. See, he solved the mystery behind the photoelectric emission, and that was the return of H, the Planck's constant. It returned with a bang to stay this time forever in physics, science, and technology completely. And it created a class for itself. What kind of class? See, in sociology, we know the doctrine of haves and have-nots. That is the way the classes are created in society. Here also, similar kind of thing was created by H. All those topics in physics which have H in it were called modern physics. And then the ones which do not have H is classified as classical physics, of course, with an exception of relativity, which is also considered to be a part of modern physics. But on the things happening on Earth, those which are having edge, those topics were the ones which are able to explained by using edge. So that's how edge came a return. And Einstein, Einstein was able to explain photoelectric effect in this way. Number one, an incident light consists of light corpuscles. When a light ray is incident on a photosensitive surface, the light is traveling not like an electromagnetic wave, but in the form of a light corpuscles. Please note, these light corpuscle was the name you used to be used during those days. It was not known as photon. Only after 20 years, that is in the year 1926, a chemist by name Gilbert Lewis, he was the one who proposed a beautiful name photon for these light corpuscles. Until the year 1926, it was addressed as light corpuscle. So Einstein told the incident light consists of light corpuscles, small units of energy. Energy of each light corpuscle is equal to h nu, exactly what Planck had told, where nu is the frequency. He had told quantas, and what Einstein told was light corpuscles. Now what happens is, when a light corpuscle is incident upon the metal, then it delivers all its energy into a single electron. See, it is going to enter into the body of the metal, and then once it meets an electron, it delivers all its energy to the electron and it vanishes. This energy rich electron, which is actually a free electron, that free electron now is energy rich. It is able to pay up the contract amount to the metal and mix and gets released itself from the bondage and comes out of the body of the metal. The amount of energy it pays up as a contract amount of the metal, that is called the work function. And then what happens? It still has some excess energy of what it received from the light corpuscle, Einstein's light corpuscle. That excess energy, it flaunts itself as the kinetic energy of movement of its own. So all this picture, that and the light corpuscle enters into the body of the metal, and then the electron receives the entire energy, and the light corpuscle loses its existence, and then it pays up some amount of energy to the metal and comes out with a remaining energy as the kinetic energy. All these were encapsulated in one equation by Einstein: half mv square equal to h nu minus w. W is the work function, nu is the frequency of the radiation, and half mv square is the kinetic energy. But now we all think that the problem is solved. But what about the physicists during those days? They were not ready. The thing is, ultraviolet rays which are falling upon the body, they are all said and done. They are waves. When the electromagnetic waves fall upon the metal, then it must blow away from there. Like how the wind, which is blowing on stones which are scattered on a surface, what happens? Nothing happens to the stones. The wind is blown away because it can't move the stones. There is no energy, concentrated form of energy to push the stones. So that way, the ultraviolet rays, which are now electromagnetic waves, they can't hit an electron. Where is the material content in the electromagnetic wave to hit the electron and knock it out from the metal? So people disagreed. They told, no, we can't take this explanation of Einstein to be true, because waves, after all, they are waves. They can't make a material particle to move. Therefore, that is not acceptable. But Einstein told, no, here they are not waves, they are quantas. They are having the energy in the form of small units, So when it falls upon the metal, then that 1 unit of one unit of energy, which we call as light corpuscle, it delivers all its energy to one single electron. So what happens is, it is something like another particle hitting electron, another particle hitting an electron. But in the case of particle and particle collision, the particle survives, the hitting particle survives, and the one particle which takes the hit also survives. But in this particular case, when the photon is hitting the electron, the photon gives its life. It doesn't exist anymore, but the energy it transfers to the electron is in such a way that it is as though another particle is hitting it. Whether the other particle is existent or not is not of our concern. But this electron is now dislodged. It comes out as if it is hit by another particle. So we must deal with this in a different way, that it is possible to discharge an electron by using the light corpuscle. That is the kind of explanation that Einstein gave. What all others opposed, who were there? The stalwarts who were opposing Einstein's idea was, number one, Millikan, who was about 10 years elder to Einstein. He did not agree to the thing proposed by Einstein at all. Apart from Millikan, Rutherford also opposed. Niels Bohr was also opposing. And eventually, later on, when the time came, Raman also opposed. So all these stalwarts are opposing the idea of Einstein. But the thing is, Einstein did not yield, did not change, because he was very sure that what he's telling is perfectly all right, and he continued to do his work. In the year 1909, he was able to he secured a job in the University of Zurich in Switzerland. He left the patent office job and he became an associate professor. But Planck himself was opposing this concept tooth and nail. See, what happened was this: Planck had told that from the black body, perhaps, he was not sure, it was all vague for him. Perhaps the black body is emitting those quantas, all right, they are having energy, but he never told that they would act like a particle. Einstein had gone one step further and he was able to tell, he told that it acts like a particle, though it may not survive as a particle after the transfer of energy. So that way, Einstein had gone ahead, one step ahead of Planck. Planck was also saying, no, that can't happen. So Planck, Rutherford, Millikan, Niels Bohr, all these were opposing Einstein. Both Planck and Rutherford, Rutherford and Millikan. Rutherford was almost the same age as Einstein, but Millikan and Planck were, they were more aged than, and they had a standing in the physics community. Afterwards, but however, the irony is, Planck had all appreciations to Einstein because of the relativity theory. So he was eager to have him in his own place. He created a chair in the Kaiser Wilhelm Institute, Physical Institute, where he was working in Berlin, and to where he invited Einstein to join, and Einstein joined them. So Einstein started working there as a German. And then I will tell you one small thing, that in the year 1960, he added one more aspect of significance to the idea of quanta, that light corpuscle. He told, because it is acting like a particle, it must be also having momentum also. It was too much for others, but Einstein, it was a general truth. On the basis of this idea that a quanta can have momentum, he went on further to develop a theory of stimulated emission, which became the basis for lasers. We know everything today that it's all true. So that was the time that Einstein went on to generate a new theory for the emission of light from bodies, like stimulated emission. But parallelly, when these things were happening, from 1912 to 1915, Millikan took interest to prove or disprove Einstein's. So he made a setup, a elaborate setup to test Einstein's equation. He made, he made a setup wherein it was all inside. It was a vacuum from external means. He was able to chop off a sodium surface. Sodium is a soft metal. It could be chopped. So you could make the ultraviolet rays to fall upon sodium surface, and the emission of electrons from the sodium surface, he was trying to find out how the electrons are getting emitted. But sodium is such a thing that it used to get contaminated very soon. So for each verification, he needed a fresh surface. For that also he made an arrangement. He used to shave off one surface after the other surface. Every time he made a observation. So from 1912 to 1915, Millikan conducted experiment, trying to find out whether Einstein's equation is all right. In the year 1912, he had made one statement. For me, the corpuscular theory of light is unthinkable. He was not ready to take in the idea of Einstein. He went on meticulously measuring the photoelectric current, and finally, in the year 1916, he did not have anything else except to say that equation of Einstein is all right, but he told idea of quantum by Einstein is not all right. He was not ready to accept the idea of Einstein's idea of quantum. He thought his apprehension was this equation is all right, contrary to my expectation, it is working all right. But the idea of quantum, I can't accept it. Maybe somebody is going to work out another acceptable theory for the same equation. So for the time being, let us leave it. So that was his apprehension. But anyway, the thing was, he gave a verification certificate. That's enough for Einstein's. So the opposition to Einstein's work started crumbling. So slowly people here and there started accepting Einstein's work. All stalwarts continued to oppose, but behind them, smaller people started accepting Einstein's. Maybe he's right because his equation is working all right. So that way. So experimental results showed mounting evidences favoring Einstein's ideas of light corpuscles. By this time, the Einstein's work and other works conducted on the photoelectric emission, they were all on the radar of the Nobel Committee, where they were observing carefully about the implications of Einstein's work. They thought, enough is enough. Let us not postpone awarding the Nobel Prize for Einstein. Let's award the Nobel Prize for Einstein this year. So in the year 1921, the Nobel Committee decided to award Nobel Prize to Einstein. But yet, they were careful. They diplomatically formulated the statement why they are awarding Nobel Prize to Einstein by avoiding the use of the word light corpuscle. They told that for suggesting the photoelectric emission equation, they are awarding the prize, but they did not say anything about the light corpuscle. Right, Nobel Prize now Einstein was able to get. Did the other people accept it? Did Bohr, Rutherford, Millikan, did they accept it? No, they did not accept it. So all the stalwarts were opposing, including Raman. In the next year, that is in the year 19, when this is how Einstein looked when he received the Nobel Prize in the year 1920. But this was the way his appearance was. Okay, now 1922, Niels Bohr got the Nobel Prize for his work on the theory of hydrogen atom structure, but he dismissed the idea while he was delivering the Nobel Prize talk. He dismissed the idea. He made it a point to dismiss the idea of Einstein, that idea, the quanta idea of Nobel Prize, Einstein should not be taken seriously. Right? How about Millikan? Millikan had conducted the experiment contrary to his own expectations. Einstein's theory worked, but he had done some other pioneering work also. He had determined the charge in the electron by using his famous oil drop experiment. Considering both together, the Nobel Committee decided to award the Nobel Prize to Millikan. So when the time came for Millikan to give his talk on the occasion of Nobel Prize, he had to tell something about photoelectric emission. He considered that against his own expectations, the Einstein's equation worked, but he stopped. He fell short of telling that his experiment proved the corpuscular nature of light. He was not able to tell that. He stopped there. So still in the year 1923, the Einstein's idea of quantas or the light corpuscles, it required big support. There was no big support for the idea of Einstein, but the big support did come. It came from the announcement of Compton effect. Very soon, Compton published his paper proving how the X-ray quantas were not dealing with the free electrons, but they were dealing with the bound electrons. It shook the electrons which are moving around in their parent, in the parent atoms, the bondage. So Compton effect give the boost. Compton effect give the final boost to the idea of Einstein. That became a deciding kind of thing for Einstein's idea of quantas. But then following that, even Raman's effect, Raman effect gave the backup for Einstein for the proving the Millikan's the Einstein's idea. So Compton picked up his Nobel Prize in the year 1927. Raman his in the year 1930. That finally gave the boost to the idea of the Einstein's proposal of Einstein, the photoelectric effect. This is the photo taken when Millikan visited our Raman Institute somewhere in the 1950s. Then he told, I spent 10 years of my life testing that the 1905 equation of Einstein, and contrary to all my expectations, I was compelled in 1915 to assert its unambiguous verification in spite of its unreasonableness. He still told it was unreasonable, but it's happening. Since it seemed to violate everything we knew about the interference of light, he was not able to accept that. So Millikan, what happened was later on in the year 1949, Einstein reached the age of 70 years. At that time, Millikan was 80 years old. A committee was formulated to pay tribute to his Einstein's work. For that, Millikan was made the convener. Millikan happily accepted that. Then he told how great was Einstein's idea. From 1905 to 1923, he was a man apart in being the one or almost the only one to take the light quantum seriously. So that way, Millikan paid the tribute to Einstein's idea. But the point here is Planck's idea of black body radiation, in which he proposed the quantas to play a dominant role, that also got a boost along with the Planck's this work. So it was not Planck. We all think that Planck's law started the quantum revolution. No. Planck's, actually, yes, Planck's equation started the quantum theory, but actually what happened was with the Einstein's idea of light corpuscles, the quantum revolution started taking place in the field of physics. The physicists and other people came to know about this quantization, not through Planck's law, but through the photoelectric effect equation of Einstein. That is the genius of Einstein. So the credit of starting quantum revolution goes naturally to Einstein and not to Planck as such. Now, Millikan is telling that he was not right. Now, what do you say regarding Millikan? We can't say anything, but Will Rogers, some philosopher, had told, good judgment comes from experience, and a lot of that comes from bad judgments. So that's exactly the kind of thing that happened to Rutherford. Will Rogers' philosophy is now reflected in the case of photoelectric emission. Now, the next thing, see, regarding knowing about the greatness of Einstein, let me express this one. See, Einstein was a Nobel laureate, but for the stature of Einstein, winning a Nobel Prize is not a great deal. If you have an overlook of the entire 20th century, there were more than 700 people who won the Nobel Prizes in different fields. This 20th century saw more than 700 Nobel laureates. So we can't estimate the Einstein's greatness by looking to the fact that he won the Nobel Prize. But in the year 2021, the Times Magazine of USA, it conducted one survey. They wanted to know who was one single individual who influenced the world's activities, the world in one way or the other the most. When they collected that survey around the globe in all the intellectual circles, one who was found out to be the person who influenced the entire 20th century most was Einstein. That was Einstein. So that's how we must understand the greatness of Einstein. So now with this, I would like to conclude my talk on this celebration of the centenary of photoelectric effect. I take this opportunity to thank my dear principal, Dr. M.U. Ashwath, my dear Dr. D. Nagaraj, HOD of Physics, my dear Mr. Narasimhamurthy, Dr. Narasimhamurthy, convener, and all the staff were all dear to me, the Department of Physics staff. That way, I would like to conclude my talk. Now, anything to be clarified, please? There is one question by Mr. Rajendra H.J. How the value of Eggplants constant can be calculated. See, this one is already known very well. The experiment is also being conducted in our laboratory classes. So I think that need not be addressed now at in this particular context. So Mr. Rajendra, I think you can please refer to, there are so many ways value which could be calculated. Even in the Millikan's experiment, there is one way that one can, by the finding out the slope of the curve, one can evaluate H. So that is my answer. Next. Mr. Dr. Gurunath KB, the question is same. What on the basis of Planck's constant H can be calculated? This has been done long ago by Millikan himself. He told that this is the way we can evaluate the value of H by taking the slope of the frequency versus the kinetic energy of the electron. I mean, we plot the graph of the frequency versus work function, the energy. Okay, by finding out the slope of the Millikan's, Millikan's experiment of the equal to UH, frequency versus energy, the kinetic energy of electron, we were able to calculate. So these are the two questions. Beyond that, if there are any more questions, please see.
Recently, the difference in the concept of the photon on used by Planck and Einstein and by Bohr. Dr. Joseph.
See, this is a question from Dr. Joseph. What precisely is the difference in the concept of the photon as used by Planck and by Einstein and by Bohr? See, we could rather take the difference between Einstein's concept and Planck's concept. In the case of Planck, what he thought was the black body is not emitting electromagnetic waves. It is emitting wave energy in terms of small packets of energy. So that's how it, but he never told that they could act like particle. Regarding Einstein, he went one step ahead, as I told, but when this light corpuscles fell upon a recipient electron, they deliver all the energy, like one particle hitting another particle. That's how the energy is delivered. But in the case of particle-particle collision, what happens is one particle survives, both the particles survive, but there is a transfer of energy from one particle to other particle. But in the case of photon, what happens is the incident photon vanishes. It sacrifices its energy for the sake of the other particle. The other particle which gets the hit, it inherits all the energy to itself. So that is the difference. That particle doesn't survive here. That is the kind of verification I would like to give. What is the fundamental difference between matter and energy? See, that one has to go to the relativity theory where A equal to mc square, where matter could be converted to energy and energy could be converted to mass. But that's the kind of thing which could be thought of. But the basic problem here is how the electromagnetic waves are able to deliver the energy to a particle like that. As such, the electromagnetic wave cannot do anything with for the other particle in terms of deliverance of energy, but the photons can do it. They are not electromagnetic waves by nature, but they are packets of energy which is having the wave content to the extent of having the frequency. So E equal to h nu, the nu is the quality of the wave which the photon is having, but they are not waves themselves. How to apply the law of conservation of spin to photoelectric experiment? I don't know really how the conservation of spin could be applied to photoelectric. Here it is a question of the energy transfer, but how could the spin play a part? It is the energy that is carried by way of spin. I'm not very well aware of this. So this one I can't answer by Dr. Mahesh. Dr. Kaushal. Kausalya. Dr. Kausalya. This question is from Dr. Kausalya. The question is, Planck's law proved photoelectronic effect, Einstein's for its interpretation. Planck's law proved the photoelectric effect. No, Planck's law did not prove. Planck did not do anything regarding photoelectric effect. He only proposed the idea of quantas, that's all. But photoelectric effect came to light only after Einstein's work. As a matter of fact, when Planck gave the theory, there was no development of photoelectric effect, because after 1 year, that is in the year 1902, Leonard published his 3 important observations. So to that extent, there's a difference.
Can photoelectric effect be?
This is a question from Amar Bashir. Can photoelectric effect be applied inversely? Can photoelectric effect be applied inversely means, but yes, see, my colleagues are suggesting that yes, it is through X-ray production. X-ray production.
Fast moving electrons, they produce electrons.
Okay, yeah. During, X-rays are produced where the energy is converted into the X-ray photons. So, Mr. Bashir, you have the answer for this. Answer is suggested by my colleagues. I'm no more in the department anyway. The answer is this. Very good answer. Here, a fast-moving electron, the kinetic energy of the electron is converted into the X-ray photons. So it is possible. Okay. So thanks everybody, thanks everyone who has attended this seminar, and I'm very happy to have given this seminar in my parent college. Thank you all for being with me.
Dear participants, hope all of you have enjoyed the talk. So, first discovered photoelectric effect, Einstein explained the physics of it. But sir, today you gave us the detailed history of photoelectric effect. It is always interesting to know the background of any discovery and stories related to it. So photoelectric effect is not an exception to this. Sir, you have enlightened all of us with your unique style of teaching. Thank you very much, SPB sir. Now is the time to listen to our second speaker, Dr. H.S.S. Ramakrishna Matte, scientist, Center for Nanoscience and Soft Matter Research, Bangalore, is now going to talk on an overview of new generation solar cells. I now invite Dr. Raghavendra UP, Assistant Professor, Department of Physics, to introduce the next speaker of the session. Thank you. Over to you, sir.
Good afternoon, everyone. I'm really pleased to introduce Dr. Ramakrishna Matte. HS Ramakrishna Matte joined as a scientist at Center for Nano and Soft Matter Sciences, Bangalore in January 2017. He obtained his master's in chemical sciences in 2009 and a PhD in solid state and materials chemistry in 2013 from Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. And very interestingly, his advisor was Professor C.N.R. Rao. Dr. Ramakrishna served as a postdoctoral fellow from March 2013 to March 2015 at Northwestern University, Evanston, United States. And from June 2015 to December 2016 at Department of Physics, Humboldt University, Berlin, Germany. Now I request Dr. Ramakrishna to take over the session.
Thank you. Thank you. I hope I'm audible.
Yes, sir.
Yeah, perfect. So I'll be sharing my screen and please let me know if there are any concerns. Are my slides visible, sir?
Sir, your screen is viewed. Please go for second slide for verification, sir.
Are
One more,
my
sir. Oh, thank you, sir. Slide is moving. Please start from first slide, sir.
Yeah, perfect. I really thank the Bangalore Institute of Technology and the organizers for giving me this opportunity to interact with you guys. Today, as I understood that I'll be mostly talking with people who are in first, second, and third semesters of engineering, and then they want to give me an overview of the implications of the photoelectric effect and really what made them different in our lives. Because most of the times what happens is we always use the product and we forget the basic invention which has resulted in that. I mean, for example, people who are talking about GPS won't remember the contribution of Einstein theory of relativity. So, in a similar way, that I mean, of course, we are using in day in and day out. In a similar way, most of the times we really forget to acknowledge the importance of the fundamental science, but more concerns about the technology which has come out of it. So, but it is glad that the Bangalore Institute of Technology has taken this initiative of correlating both the fundamental aspects and the applied aspects. And I was asked to talk about the applied aspects of it, where the previous speaker has given you the fundamentals on how the photoelectric effect and the historical perspective of it. Because every time to really know the feel for exactly what the science is all about, unless until you know the history of it, you don't really feel for it. So in that way, I'm glad that this program is designed in a unique way where you're talking about the fundamentals as well as the applied aspects of it. So probably I'll try to I know it is not going to be easy for me to uh, convey what I really want to convey, particularly knowing you are from the background of I mean, just finishing +1 kind of a thing, +2. But I'll try my best and try to bring up the some of the fundamental things that we learned in our +1, +2, and how those will be how those things will enable you to devise make them more efficient. So for that we need to really clear about we need to be very clear about how the electronic structure changes and what are the different materials and how this what are the different types of semiconductors, what is doping and p-n junction. These are the three aspects which you might have heard in your classroom, either in your BTech initials first and second semesters or in your +1 +2, so to some extent. But I'll try to tell them in a slightly different way, but not very different, but putting from a device perspective. And then I'll try to give you an very action to solar cell, like how one would characterize. I mean, somebody gives you a solar cell, right? Be it any solar cell, doesn't matter. How one would characterize it, and what are the parameters that one should characterize it? What are the parameters that you need to know? I mean, you know that for everything there will be some kind of requirements, right? I mean, if you want to attend for IAS exam, then you have to say that okay, you need to finish some masters or bachelors or something like that, right? For everything there will be some kind of qualifications, and then you essentially for solar cells also, to say it is good or bad, we have some parameters which is defined, and those parameters will be discussed. And then I'll briefly gives you about what are the different types of solar cells. The most common one which you are seeing in and day out is this silicon one, which is a black panel or bluish black kind of a panel, which are on our households or on deserts. I mean, you might have seen in many places. And then what are the upcoming new generation solar cells? So I'll be discussing briefly about it. And then most likely I'll be ending up the talk with discussing more on organic solar cells, which is our area of interest, where we really work on those aspects. Our group is expertise having the fabrication and measurement of organic solar cells. So I'll try to end up with that. Yeah. With this, I'll just go to the brief introduction. And this is something which is very interesting and important. You see this, the one which you are seeing on the left hand side. One second. Yeah, you see what you're seeing on the left hand side, which is like the requirement of the energy and the world population growth. So if you see, the world population is increasing, and the world energy consumption is also increasing. There's nothing great about it, you know. I mean, we know that when the population increases, world energy consumption increases, because more number of people, more number of power. Instead of one mobile phone earlier in one home, now we are having 7, 8 mobile phones. So it means that there will be some more power, and even we have a lot of devices, right? But what is alarming is this: the population of these industrialized countries are remaining the same. It means that the countries like us, like the developing countries, are the one who is going to have the majority of the increase in population. It means that we will be demanding, we will be requiring more of the energy than the other people, because our population is increasing than the other industrialized countries. And with this in mind, currently the global energy consumption, of course, these are old statistics. I don't really see much difference now, and I really hope that the COP26 and then other Paris Agreement would really enable us to do it in a slightly different way, reducing the depending on fossil fuels, and we really hope for that. And I really hope that India also contributes significantly in this direction as well. So if you see, the most of the fossil fuels, be it whatever it will, oil, gas, whatever, these are all compute to 87%. Only 13% are coming from the other non-renewable, other renewable sources. So now what it means is, uh, down the line, at some point of time, when you're talking about non-renewable, it will soon get exhausted. So what happens? And not only that, it is also very important to know that it is important for any country not to depend on others for your daily life. If let us assume that there is some quarrel between India and some other nations, and then we are importing a lot of oil from them, and they say that from tomorrow onwards we are not going to give oil. And to my knowledge, if I'm not wrong, please don't take it me the number of the days what I'm saying. But if I'm not wrong, the reserves what we have in India with respect to strategic reserves might serve for 7 to 10 days. I'm not sure. I could be wrong in that. But yeah, I mean, even if it is a month or 2 months, let us assume that. But still, after some time, we'll be depending on this. So it is always important to be self-reliant with respect to the energy. So that's what our intention, particularly all of us should work in a direction. How do we reduce our depending on the nations where we don't have these oil reserves, but we still need a lot of energies? Of course, there are very large number of issues that one would end up with when you have these renewable energies. Non-renewable energies, you'll end up with pollution, the climate change, and this environmental loss when you're looking for mining. I'm not getting into these details because you might have heard all those things at some point of time in your college days or wherever. But what are the other alternatives? What are the renewables available? I mean, you might be knowing that in 2004 or 2006, we have this impact with this nuclear treaty with the US, which is about the nuclear energy, which is also good, but obviously there has some its own concerns. And hydroelectric power is good, but at the same time, you need rivers and other infrastructure. Of course, these are all good, but still, what our interest is to see whether we can use the solar energy which is available and which can help us to charge our batteries, charge our mobiles, vehicles, and all. So our interest is to focus. The background that what we have is probably we could contribute from the solar energy perspective, and where the basics are something which we will be discussing now. So our interest is more towards the solar energy. Of course, there are many things one would be looking from a nuclear energy and hydroelectric power concern, but probably my expertise won't allow me to talk on those aspects. So coming to the solar energy, this is one of those things where it has powered life on Earth for many millions of years. I mean, I don't have to tell you these things. It's an originated from thermonuclear fusion reactions occurring in the sun. But what is important is the power output per second is 10 to power 20 megawatts. It is more than sufficient for all the for all the, I mean, all the habitants of the Earth to survive for a long time. So, but what is this solar radiation? Again, I'm trying to correlate these things with what you have learned and what you're going to get slightly new things from this talk, if at all, if I make any sense. So the electromagnetic radiations are have from this one range from gamma rays to X rays, ultraviolet, visible, infrared, microwave, and radio waves. what we will be talking more or towards the range, what we're talking about, the visible range. So if you see the whole solar spectrum, as you are seeing here, you have the total component in this solar spectrum is this from, it's in micrometer, but you don't have to worry about it. It's around 300 nanometers to 2500 nanometers. So the UV light component, the light that we receive from the sun, you'll have only 5% of the UV light. It has 46% of this visible, and you have 49% of infrared, near infrared, infrared kind of these things. So our interest is to whether we can use this light and convert them to energy. I mean, the light to electricity. That is what is nothing but a photoelectric effect. Photo is nothing but light. Electric is like how can a photo, or how can a light can generate electricity is all about this effect. So which we will be talking in detail in the next couple of in the next 25-30 minutes. So before knowing into this photoelectric effect or using this photovoltaics, it's what is called photovoltaics. That's the other name of the solar cells. Photo is what it gives the light, and voltaic is nothing but the voltage. If you can generate the voltage using the light, that can be used for powering your devices. So when you want to really understand how these photovoltaic devices works, there are certain parameters that you need to keep in mind. What are those parameters? So you can see here. So zenith, or the one which is sun, is here and earth is here. As you know that when you have these rotations and revolutions of the earth, you will have this movement, and then the movement of earth will not be stationary. Because of this, we assume that I mean, when it is moving, the angle in which the radiations reach to the sun would vary. It means that the intensity also would change. So for that, people have already defined what kind of intensity of the light that one would receive, or what is the spectrum, how the spectrum of the light would vary with time to time, okay, or at different angles of sun. So now what we are at is, when your sun, when it passes through this vacuum till you get the atmosphere, the intensity what you're getting is what we call as AM0. After that, AM is nothing but air mass. This air mass has to travel till to the reach to the earth, on top of the earth, up till to the surface of the earth. Then if the angle is straight, if there is a 0 degrees, okay, from the angle between the sun and the earth, when we call them as AM10. And what happens if the position of the sun, or I mean relatively the sun position or the earth position changes with each other? If it is at 48.2 degrees centigrade, we call them as AM 1.5. It means the kind of atmosphere that the light has gone through will be different. If it is 60 degree, it will be what we call as AM20. Why it is so important? Because when we are developing any devices in the laboratory, you may not have the sun all the time, and you wanted to really have, sometimes if you measure, let's assume that you fabricate one device in India. We have so much sun. I mean, on that it's probably a really summer season, or you are in Rajasthan or some other place compared to Himachal Pradesh. So obviously the intensity and the temperature would be different. So the solar cell efficiency you'll never able to standardize it. So you claim that you have a device of really high efficiency. It means that I mean, let me tell you clearly what is an efficiency of a device. It only tells you how much light, if you shine on your device, how much electricity you will get it. That's the only thing. The number of photons, you might have heard the word photon, right, which is the pack of quantum of light. So the amount of photons that you shine on your device, how many of them would be absorbed and how many of them would be converted into the electrons or the corresponding electricity. So that is what is nothing but a photo conversion efficiency. So if you are shining different amount of lights, you will never know what is the standard efficiency. So you make one device in India, and somebody makes another device in Russia, and you claim you have an X efficiency because you have a different sunlight, and the other guy claims has a different efficiency because he's having different sunlight. So how do we say that who is right or wrong? Because both of us are right, but unfortunately we don't have any standard measurements to recheck or confirm what I am saying is correct or what the Russian guy is saying correct, or for that matter, American or European, it doesn't matter. I'm just taking for an example. So for that reason, we have set a standards called AM 1.5, which is a laboratory simulated one, which is taken as 48.2 degrees centigrade. I mean, which angle is between that. So from now onwards, whenever we simulate any radiations, when you are trying to test your devices in the laboratory, what we call them, we use a light, what we call them as a solar simulator, because we are simulating the sun. That's what we call it as a solar simulator. The conditions for the solar simulator would be equivalent to AM 1.5 radiations. As you're seeing this, this is how a spectrum of AM 1.5. Now, when you are under these conditions, AM 1.5 radiation, it doesn't matter whether you're working in US, UK, India, doesn't matter. You can obviously have a benchmark or a reference system to compare among two different devices so that you can understand the fundamental aspects as well as the application aspects of it. So the other aspects, now so now you understand the practicality of what is the importance to define the air mass. It is just to see that whether you are if somebody wants to reproduce your results, even the laboratory thing, this will help. And of course, in the field conditions, it will be entirely different. That's we are not talking about. So the other part is, whenever you talk about the radiation, as you know, there are only three phenomena which can happen. Either it could be scattered, reflected, or the one which reaches to the earth. So even then, there are some components. When the incoming solar radiation, which is 100%, most of them here, if you can clearly see that, so only the 20% of the light radiation would be absorbed or it will come to the surface. So out of which 4% would be reflected back. And in this case, and if there are other reflections, when you are talking about the light which is getting scattered, now we talked about the reflected light. And if you're talking about the scattered light, even from this percentage of the scattered light, 6% will be upward scattered and the bottom will be 6% will be bottom scattered. And even if you see this, 30% is lost to space when the sun is coming. If it is having 100 photons there, by the time it reaches the atmosphere, that time itself it loses 30%. Of course, these are the things which will give you a clarity. And at the same time, these clouds will absorb something and then they'll reflect something towards up and something they'll reflect down. So there are many various aspects what happens to the radiation, whether the losses in space, the scattered and the reflecting components in the atmosphere on the surface, all those things needs to be have kept in mind. Of course, it will help you to get a feel like what is happening when the sunlight is started from the sun, what are the things happens to it before reaching the earth. So, and there are some calculations on how much power reaching the earth is around 1.37 kilowatt per meter square. Of course, variable with area depends on the other aspects. So these are the things which one need to keep in mind. Now, going to a bit of background, probably not as exclusive as what you have heard in the previous session. So the solar cells background is something like this. In 1839, a French physicist, A.E. Becquerel, first recognized this what is called as photovoltaic effect. By now only I told you photovoltaic means you shine the light and you see some voltage. It's something like you go to market, you give money and you buy some goods, right? You want to buy rice or whatever. So for the money that you give, the corresponding goods or the services that you receive. So that's what we call, in a similar way, is photovoltaic is nothing but photo is what you are shining, and the voltaic is the one which you generate using the photo. So that's what photo is, the one which you are giving to the system. Voltage is what is giving, the system is giving back. So if you can get as much as voltage as possible or as much as the current that is possible from the system, it will be always helpful for you. And in 1883, it took some time, where the first time they built this kind of solar cells, which is coated with semiconductor of selenium and an extremely thin layer of gold to form the junctions. Don't worry about it, we'll come to it in detail. But as far as the practical applications are concerned, in 1954, the Bell laboratories have experimentally found that when they're working with silicon, if you dope with some impurities, you might have heard of p-doping and n-doping, right? So that I will also be talking in detail in the coming slides. But they're found it to be extremely sensitive to light. Then they invented the practical device for converting the sunlight into useful electric power. I'm trying to put in as simple language as possible so that you will really get connected exactly what it is. And that time, the power conversion efficiency is around 6%. It means that only 6% of the light you will be utilizing, you are shining 100%, 100 photons. Among them 100 photons, only 6 of them are able to give you the electrons or the voltage that whatever you require. So that's what it is. So it means that if you want to have a good device, you wanted to have a device of 30%, 40%, 50%, so that it means that you are using effectively, so that you don't have to use big panels. Even a small panel will help you to heat your water or whatever. And in 1958, the first spacecraft to use solar panels was US satellite Vanguard 1. So this is what to give you a brief perception, like what made, who made these devices, how an accidental discovery has led to fabricated device, which is around 6%, which is still good. And then later their applications within 4 years to power the satellites. So now, before going into any of these devices, let us try to understand how our fundamental science or how fundamental understanding of these systems would enable you to make materials or fabricate systems which will be helpful for you or which will deliver the your requirements. So now if you take, so let us start with atoms. I believe that you are all comfortable with atoms because you might have reading about these atoms periodic table from your at least 9th, 10th standards, if I'm not wrong. So what happens is, if you take an atom, you'll have one atom here, right? Then what happens if you take two atoms? Okay, this is where the chemical bonding comes into the picture. So when you're talking about the chemical bonding, what will happen is you will have molecular orbital theory comes into the picture, where the two atoms will interact, and then you will have this HOMO and LUMO, which is highly occupied molecular orbitals, low unoccupied molecular orbitals. So these are the one which use the HOMO LUMO of your systems. Essentially, what it means is, when you combine two atoms, when the bond forms, it will form into two orbitals, which is called sigma and sigma star. I'm sure you might have learned these things. In a similar way, when you have 10 atoms, you will have those many atoms. You see here, because of two atoms, you are getting one bonding orbital, other one is non-bonding orbital, because you have an electron from one atom and you have another electron from another atom. When they combine with each other, you will get one bond formation, right? So those two electrons are already in this bond, which is called this in one bond, and this is called an anti-bonding orbital. Okay, so now if you have two atoms, you have one bonding and one non-bonding orbital, because it's a linear combination of atomic orbitals. If you take two atoms, you get linear combination of two atoms. If you take 10 atoms, you will get 10 orbitals, and then these are the one which is bonding and which is non-bonding. Let us assume that instead of 10 atoms, if you take 100 atoms, then the energy space even further decrease and they'll even get close. And then now, when you're talking about any solids, you're talking about one mole means, right, 6.10, 6.023 into 10 power 23 molecules, right? So when you're talking those many molecules or those many atoms in one mole or one this thing, then what will happen? You will have infinite number of orbitals coming, and then we can't differentiate individual because they are so much crowded. The line between the distance between these two lines are so small, it becomes so difficult to differentiate them. That is how you will become a solid. So from one atom you become a solid. Okay, initially you will have a single atom, it becomes a multiple atoms, and this is what we call as an electronic structure. Electronic structure is nothing but how your electrons are placed, whether it's in bonding orbitals, whether in a whether it is in lowest orbital or the highest orbital, it doesn't matter. These are the electronic structures, means where the electrons are there, as they are describing the structure of the electrons, how they are arranged, we call them as an electronic structure, which is nothing but a band theory. So now if you take any solid, it doesn't matter whether you take a silicon, carbon, whatever the material that you are around, carbon, iron, every one will have what we call, every solid will have one valence band and the other one as a conduction band. That's what we call them as names, which I'll be coming up to the later. And the corresponding density of states, don't worry about it. And now coming to the nano aspects of it, what it means is, you are not in the atom state nor in the infinite atom states, where you have somewhere in between, which we call them as nanocrystals or nanoscience, where you have so many orbitals, which means so many electronic states are possible, and at the same time it is not as a bulky. Because of this, the properties, the electronic properties are different, and the physical, because of that, the physical properties will be different. It may not be as conducting as the bulk, or it may be superconducting or better conducting than bulk. So many things will change when you make into from bulk, when you make any nano systems, because nano is something which is nothing but a group of atoms. Whether that atoms could be 100 atoms, 500 atoms, 1000 atoms, depends on the system. So that, when you're talking about, instead of 10 atoms, if I make 1000 atoms, you will get some electronic structure which will be resultant of like this. So the electronic structure of these nano systems would be entirely different compared to the bulk, because of this simple reason. If you understand to this extent, then it will be more than sufficient for us to take it forward. And now what we call as valence, the one which is filled. Here we are talking about, these are all filled with electrons, right? This is what we call this bonding orbitals, right? These are filled with electrons. The one which is filled with electrons, or we call them as the valence band. The one which are unoccupied, we call them as conduction band. So now you might have heard this something called conductor, semiconductor, insulator by now. How do you differentiate between them? So the conductor is the one where you have no band gap. It means that the valence band and the conduction band, as you can see here, this is conduction band and this is valence band. Both of them are merging. Whenever you see there is a merger between the valence band and the conduction band where you cannot separate, we call them as metals. When you have some gap, which is around 1 electron volts up to 2 electron volts or 2.5 kind of thing, so then we can call them as semiconductors. When you take the insulators, the band between the valence band and the conduction band is so high, there is no possibility of any electron who can jump from this to this. It's like if there is a 4 feet wall, you may be able to 8 feet wall, you will over it with your energy. If it is 2 feet, you may. If it is 3 feet, you may try. If it is 6 feet or 7 feet, you can still use some of the gadgets and then cross over. If it is like 1,000 feet kind of a thing, so there is no point in crossing the wall rather than flying over it. So this is how exactly when your barrier is so much beyond a point, you cannot really send your electrons which are filled here to this. When you send electrons from here to here only, then there will be some conduction. Otherwise, there will be no conduction as such. I mean, photoconduction, what I mean by. So now there is also one more concept that you need to know, what we call as a direct and indirect. Now we are interested in only, we don't talk much on those conductors and we don't really talk much on the insulators. We really only talk within the language of semiconductors, because this is the place where we'll have these electrons and holes, where if they absorb, if they shine light, there is a possibility of converting, I mean, transferring from one electron to here, and then that electron can be used for your purpose. When you take an electron from there, that will be, and it will come into your circuit, and so that the movement of electron is nothing but in current, that generated current can be used to power your devices. So now there are two types of different semiconductors. One is direct bandgap semiconductor, other one is an indirect bandgap semiconductor. So how do we differentiate between a direct bandgap semiconductor and an indirect bandgap semiconductor? By now I've already told you there's something called valence band and there's something called conduction band. If both of them at the peak position, at the bottommost position, if you see this is the top position of this and the bottommost, if both of them are having the same k value, or if they are having the same symmetric point, then what we call them as a direct bandgap semiconductors. If they are not same, if they are not lying to each other on top of each other, what we call them as indirect bandgap semiconductor. What does it mean? Happens is between the valence band and the conduction band, what we call them as a band gap, right? So what happens is if you give more energy to your system than the band gap, then that energy is through your light, then the electrons which are there absorbs that energy and jumps here. But if it is an indirect band gap, what will happen is then also it can jump with that energy. But what happens, there will be no another levels to accommodate. You see this, these are all the empty levels which you are seeing here. So if you have only empty orbital, you can fill the electron. If there is no orbitals, even if you send the electron from here to here, it will come back saying that there is no space for me to sit anywhere. Why should I go there? So with somehow it relaxes and it come back. So this is exactly what happens in the indirect band gap. Though you give energy to these people, but it cannot stay there. For that, what it needs to do is it needs to change its momentum through momentum conservation, and then it can possible. So then the indirect bandgap semiconductors also can be used for efficient utilization, but otherwise most of them will be interested into this direct bandgap semiconductors. So now coming to the silicon, as you all know, which is the fourth group element with 4 electrons in their shell. So when silicon atoms are brought together, so you take one silicon, you take another silicon. So what happens is the silicon and silicon will form, as I said, no, this is also having one empty electron, this is also having one empty electron, they'll form a bond, and when this forms a bond, they'll come into bonding orbitals, and the one which are giving the electron will become an anti-bonding orbital. So in a similar way, what happens is it comes into a geometry called tetrahedron geometry. Don't worry about it. So there are some other ways of even carbon silicon, all of them form tetrahedron geometry based on the hybridization and the chemical bond. So now if you take this as such, there are no free electrons available. Every electron is bonded. So whatever the energy that you give to silicon, from where silicon will able to move the electron. See, electricity you are getting if there is only movement of electrons. If every electron which is available with this atom or in this solid is bonded to each other, there is no way that they can move with it, that they can move within the system. So that's the reason, that's what we call them as some of the systems will not be able to conduct electricity there, because there will be no movement of electrons. So if you take at 0 Kelvin, when each electron is in low energy state, because of this covalent bond position is filled, even if you apply a small electric field, no electrons will move because they are bound to their individual atoms. It means at low temperatures, at 0 Kelvin, the silicon is an insulator. But what happens if you increase the temperature? There will be some the bonding between them will not be as this one, and there will be the valence electron gains enough energy, and if the amount of temperature that you give may help you to increase your conductivity. This is exactly what happens in semiconductors. So now this is exactly what I wanted to say. When you say when you have conductor, the band gap is very less or less than 0.0 electron volts, and when semiconductor it could be 1 to 3 electron volts, and when it is more than 3 electron volts, we call them as an insulator. It doesn't matter whatever you do, you can't really motivate those people to do any work. So insulators belongs probably to that category, that whatever you say, it's not going to be of any helpful. Of course, they're also useful in their own way. If you don't have an insulator, you can't protect yourself from the passing electricity. So everything is important in life. I mean, if you think that if you're seeing a negative connotation, it's not good, because as I said, some of the people will never respond, and that's how they become insulator kind of a thing. But insulating have its their own advantages. So in a similar way, the people who are not responding in academics might respond somewhere else. So yeah, we need to know. I mean, we don't have to see it with some lens. We don't know who will be doing good in what area. So in a similar way, insulators have its own advantages, semiconductors and conductors. Without these three, we would not have been surviving like this. So now, what is important? As I said, silicon as such, you can't use it because you don't have any free electrons. Now what we need to do, this is what we call them as intrinsic semiconductors. If you don't mind, I just need a minute. So there's something called extrinsic. So what the silicon is an intrinsic semiconductor. But what we can do is to use it for our advantage. We can make them extrinsic. The moment you make them extrinsic, they'll start becoming conducting. You know how they will become conducting? Instead of reacting silicon with another silicon, you react silicon with arsenic. So in this guy, silicon is having 4 electrons and arsenic is having 5 electrons. 4 electrons with silicon and 4 electrons of arsenic bond each other. Then there will be one left over, and this electron is available for you to roam around. In a similar way, this is because you have an excess of electrons, then we call them as N-type semiconductors. If you have excess of electrons with your system, we call them as N-type semiconductors. So because of that, your conduction, because you have a lot of electrons available, so there will be a slight shift in your these things, and then your Fermi level would come somewhere here. So coming to the P-type, instead of silicon bonding with another silicon, if you can dope some of them with boron, what happens is boron is having only 3 electrons, but silicon is having 4 electrons. So what happened again? So that there will be one empty orbital which is available for bonding. So because of this empty orbitals, if somebody can give hole, because empty, see, the hole is an imaginary concept. You only know electrons. When there is no electron, we call them as a hole. Here there is one vacancy is there. Because of that, you are generating a hole. Instead of excess which is there, I have an excess electron. Here I don't have an electron from the boron to bond with silicon. So because this bond will have an empty thing, that's what this becomes like a hole. So this conducts P-type, which is nothing but a holes. So this conducts, this is what we call P-type. This conducts electrons, this conducts holes. It conducts holes is nothing but it can accommodate electrons, or there is no electron available, nothing more than that. And now what happens? You have this P-type and you have this N-type. Then you take this P-type material and you take this N-type material, combine with them. Then what we call, we'll end up with a P-N junction. When you put P material and N material, P-type material and N-type material next to each other, then we will end up with a P-N junction. When you're talking a PN junction, you can apply the voltage or the bias either in a forward direction or the reverse direction. What I mean to is forward bias or reverse bias. In the case of reverse bias, the N-type material will have a positive voltage and the P-type will have a negative voltage, whereas this one. So because of that, because of this voltage, applied voltage, which is under equilibrium condition, P and N-type will be like this. But under applied conditions, which is the reverse bias, all N-type will go there and P-type will be go there, and there's a lot of depletion layer which is forming in between, which becomes a barrier. See, the whole idea of this is you apply some potential, you want your electrons or the holes to move from this end to that end, and you want to generate the electricity. But what happens is, I mean, you want the movement of these ions from this side to that side. But when you have such a big depletion layer, because you didn't apply your potentials well, this region in the reverse bias, you don't really see any current. This is what exactly. Then after that, you might have known about after beyond a potential, there will be some breakdown voltage and there is avalanche current. All those symptoms you might have heard in your +1, +2 kind of thing. This is the region where it comes up. At that time, your device will break down. So then you don't want to use them. But how you do is you bring a P-type material, you bring an N-type material, and you apply a forward bias, and then you see you are having with increase in potential, you are increasing current. This is exactly what you want to use for these things. When you have these PN junctions, they have applications in. In PN junctions, the current is allowed to flow in only one direction from P-type to N-type materials, and these have applications in transistors, solar cells, LEDs, photodetectors, diode lasers, everywhere. So whatever the simple concept that you're doing, what you're doing is nothing but an IV characteristics. It's the I means current, V means voltage. Or we can sometimes we call it them JV characteristics. J means current density, which means that the current you have to divide with the area of the device. So that's what we call them. So typically this is how, if you see the forward bias, this is the device or the solar cell characteristics. If you make any PN junction, this is how a device would look like. The characteristics of a device would look like. This is in the absence of light. Now our interest is what happens to this PN junction when you shine the light. This is exactly what we will be interested in. And how do we increase the performance of this device? By manipulating the materials to make them more efficient. Now, I've shown you how a JV characteristics of a solar cell would look like, which is in the dark condition. The moment you shine the light, instead of, let us assume that it is in the first quadrant, now you will become into fourth quadrant. Then there are four parameters which comes into the picture, where it is meeting x-axis, what we call them as open circuit voltage, where it is in meeting y-axis, we call them as short circuit current, and the power efficiency is nothing but multiplication. Volt current is nothing but the power. That's what you get. Typically, you get is the maximum power efficiency that you get theoretically. But what happens experimentally, whenever you do whatever you are supposed to get theoretically, you won't get. But if in principle, what happens, you're supposed to draw a square, which is the power that you can generate from your device, which is nothing but voltage into current. But what happens is your box will never be as square as this. You will have a characteristics like this. It means that there are some losses happening in your system. Those losses will be defined using what we call as fill factors. What we call them as fill factors. Fill factors is nothing but it will give you how much square is your device, how much efficiently you are able to collect your charge carriers or generate your charge carriers. So finally, the power conversion efficiency is nothing but the P max, which is here, because it's a place where you'll get more voltage as well as more current, divided by the light you have shined. Then the power maximum can be converted using this multiplying with JAC, VOC into fill factor by initial power. So these are the parameters that we typically use for characterizing a solar cell. Now we are talking about the losses, right? So we'll try to understand what are those losses. See, the whole idea is you are shining the light, and when you shine the light, if that light is having enough energy, if you are having a semiconductor, if the energy is more than the band gap of your material, then the electron which is in the valence band will go to conduction band. And now what happens is when you separate this electron, and when what I said is when you send an electron from valence band to conduction band, when there is empty orbital band, we call them as holes. So it means that what you're doing is by shining the light, you are making an electron hole pair. The electron is now in the conduction band. The empty orbital we are calling as a hole because there is no electron as such. That's what we are calling as a hole. The electron hole pair is being generated. Now your job is, if you leave like that, electron wants to come back and sit in the original position. Now what you do is you do something and see that these electrons and holes are not combined and they're separated. Then what happens? You are taking the electrons from the material and bringing out. Those electrons are available for you to give you the corresponding conversion efficiencies. So now this is how exactly what happens. You have a p-type material, you apply this energy, then what happens? You have your this one your this things, then it goes out. And if you can put another material, see, now what happens is the electron will recombine, right? If you shine energy, you have your electron here initially, but the moment you shine the light, it goes there. But otherwise the electron always want to recombine and come back to its original position. That's what its most stable state is. But that if that happens, you will not able to generate any electricity. Then what you need to do, you need to show this electron to reduce some of its energy, because this is the energy scale. If you have high energy, it will not be happy, you want to come always to a low energy. Then what you need to do is, if you can put another orbitals here, that's what I said. If there is an electron, if there are no orbitals, electron don't know how to move without an orbital, because electrons are always in orbitals, right? So if I can put one more orbital, and if this electron can goes to here, then we will be in a position to generate the voltage between the difference between this energy, and these electrons will be calculated. So during this process, you will have a lot of losses, what we call thermalization losses, which means that the radiation may not able to excite the electrons, or there could be losses with respect to junction, because you have a junction here. Some of them may not go, they may recombine here itself. Or contacts, you are taking some contacts to collect the electrons here, those will be contacts. Or when moving from here to here, you may also end up with the recombination, because we don't know when they can recombine, because recombination is always a good thing for electron and hole. So these are the losses you will have in the cell. So if you know these things, now with this fundamental aspects, probably in the next 10-15 minutes, I will be giving you brief, with these basics, we'll talk about the real world devices, how a silicon solar cells, what are the different types of silicon. See, when you see silicon solar cells in the market, there are different types of silicon. Some of them are what we call them as monocrystalline silicon solar cells, some of them are polycrystalline silicon solar cells, and some of them are amorphous. See, the reason, the difference is, monocrystalline means you take one, if you take one what you call one paper, one A4 sheet paper, and you use it as such, okay, what we call them as a monocrystalline silicon, and all of them are having same thing. I mean, just giving an analogous. Now you take the same paper, you cut into pieces and then stitch it. Single piece is crystalline, but all of them are arranged in different. That is what we call them as polycrystalline nature. The amorphous nature means it is not even crystal at all. So what happens is, if your system is not crystalline, the bands which I've shown you previously, those are not well defined. When you don't have well defined bands, it means you don't have well defined orbitals. When you don't have well defined orbitals, it means that you cannot conduct electricity. So now when you take monocrystalline, the conduction, the conductivity of them will be very high, or you have less resistance. In the case of polycrystalline, you will have intermediate. In the case of amorphous, you don't much have conductivity, because there is no defined bands for your electron to move around. This is what because of that, when your electron is not able to move, then the efficiency decreases. So monocrystalline silicon solar cells will be very efficient compared to polycrystalline and compared to amorphous. And of late, there are people from last 10-15 years, people are working, maybe even 20 years, people are working on other categories called Dyson solar cells, hybrid organic and organic solar cells, and organic solar cells, which I'll be discussing with you in some detail. So the monocrystalline silicon cell, as I said, is produced from pure silicon, which is a single crystal, and it is having an efficiency close to 14 to 17%, whereas the polycrystalline will have 13 to 15, and amorphous is having 5 to 7%. So now, as I said, there are different states in which the solar cells work. If the stage one, when you shine the light, you have your valence band and the conduction band. This electron hole pair will be generated from your valence band to conduct band. In the stage two, the valence band, the electron which is coming here, which you are shining here, these electrons will come over where the electron hole pairs will be separated, and then this is a movement, and then use them for your power. Because if you put, you are generating these electrons here, you give the right load, this load will take, and you will generate the using that one, you can operate your device. So how these crystalline silicon cells are fabricated? Because of this fabrication process, it becomes expensive. But of course, there are a lot of improvement in the process. That's what we are seeing an increase in trend that people are using silicon solar cells, because now the technology is almost getting matured, or to some extent one may say it is matured. So because of that, the prices are getting reduced. So you have to take a silica, which is nothing but a sand, as a raw material. You have to purify it, you have to crystallize it, and you have to make them as single crystals. Once you make the single crystals, you have to cut down into thin silicons, and then those raw wafers will remove all these dust and other things. You need to do this surface texturing. The surface texturing is important, because if you have a surface texturing, it will help you to absorb more and more light. And after that, you have to do the doping and diffusion, otherwise your conductor will not be good. After that, you have to do some anti-reflective coating, so that you will have better light absorption. After that, you have to give contacts for current generating the for collecting the current, which is acts as an electrodes, and then you will have a final cell. So this is how a schematic on the side it would look like. The small one, what we call them as cell. If you have so many of the cells, we call them as modules, and these are called an arrays. So this is how a crystalline silicon solar cell would be fabricated. And this is a process which I'm not getting into detail, but what happens is, when you're talking about the crystalline silicon cell, it will become, once, you might have seen, if somebody throws a stone over crystalline silicon cells, it will break. Once it breaks, it will not work. So that's what people are interested to make amorphous, so that not only in terms of mechanical strength, but also it will give you an additional features, what we call them as a flexible. So here you are seeing these flexible silicon solar cells, which are being produced in large scales. Okay, so this is a process where I'm not interested to discuss here, but otherwise, essentially what happens is, people are also fabricating a lot of flexible silicon solar cells. Then you can put it on your wristwatch, you can put in your on your doors, wherever you want, and it will be really useful for you to reduce some of your electricity bill. Of course, they're a bit of expensive as of now, but still, in down the lines, it will be useful. The other one is the Dyson stage solar cells, which is invented by this person who is in this picture. So these are a kind of a new concept. What it does is, you have an transparent conducting electrode. Maybe I'll go to this slide. What happens is, instead of silicon, because there should be some material in your device which should absorb light, right? So far we are using silicon to absorb the light using the band gap, and as it doesn't conduct, you make it an extrinsic semiconductor, and you do as much as possible, as I said, that surface structuring and other things, to absorb more and more light. So in a similar way, then instead of silicon, if you can take dye, which is nothing but a color, or paintings that you see on your wall, right? If I can use the dye molecule to absorb the light, and then if I can fabricate a solar cell, because it absorbs much better than other things. So people have looked into it, how I can use these dyes for making solar cell. That is what it is called as dye sensitized solar cells. The role of dye is to absorb light, and then you do your device fabrication in such a way that after the light absorption, you will have your electron and hole pair formation, and then you fabricate your device, or you put another materials in such a way, because they said the electrons has to move, means there should be some orbitals, otherwise they will not be able to move, right? So those empty orbitals are the orbitals which are of equivalent energetics. You will be provided with another materials like the TiO2. Then you will be in a position to make a Dyson stage solar cells. This is exactly what we have shown here. Of course, instead of dye sensitized solar cells, the counter electrode could be varied with another dye, and this you don't have to worry about it. But essentially, the concept is how much light you absorb, how much of them you can convert it into electrons, and how much of what is the efficiency of doing this. One way is used to dyes and making them convenient to convert this electron hole pair without even getting recombined. See, when you recombine, only the light will come. The light which is coming up is nothing but the photoluminescence, which is nothing but the color that you are seeing. If you are seeing the color, it means they are recombining. But if you want to really use it for solar cells, they should not recombine. That's the reason we put another levels to make it work better for you. And there are a lot of people who are working on hybrid solar cells where you will use quantum dots, where I said this is particularly nano, where you have a bit of high absorption coefficient. When you generate electron hole pair in this layer, you use TiO2, which is actually acts like a buffer layer. It will only take electrons, it won't take any holes. So what you do is you generate electrons and holes. You put one layer which only can conduct electrons. You know this osmosis and the reverse osmosis, right? In a similar way, here you have a similar concept where you, basing on the energy levels which are present there, either this guy can conduct electrons alone or hole alone. But the TiO2 essentially conducts only electrons. So this guy, basing on the interface, you can collect your all electrons here, and the holes will collect from the bottom, and then you'll finish the circuit, and using this you can generate the power. But now maybe another with another 5 minutes to stick to the time, I'll try to finish on the solar cells, organic solar cells aspect of it as well. So now what is happening is, in silicon is an inorganic component, and as you might have seen in the previous process, it is very difficult to process. You have to take silica, I mean, you have to take sand and you have to convert it to silicon. And that's the reason it's all expensive, and it involves a lot of high-end technologies. So now can we use small molecules, like small, I mean, instead of small molecules, if I can say plastic, which is nothing but a polymer, can I use plastics the way you are using dyes, right? See, you're seeing some plastics are also uh, absorb light, right? That's the reason that they are having whatever the color, whatever you're seeing. Of course, that is coming from dye, but you can make those plastics to use for your purpose. So, no, but what is the problem is, the plastic is not the one which conducts electricity. That's the reason you will not get shocked when you touch. I mean, you can't pass current through a plastic or a polymer. But one could make polymers which are conducting. That was also given a Nobel Prize. So now what people are interested is, instead of using silicon, can I use a small molecule like an organic small molecules or polymers? Usually they're not conducting, but if you can make them conducting, which is a conducting polymers, which itself is a field of interest, and then it's been already awarded Nobel Prize for inventing them. So then it will be really useful, so that you can it will become as cheap as the plastic bucket that you can buy, because essentially you're using the same material, right? Of course, now it is kind of challenging to make them conducting. Of course, these are fundamental issues to believe. But the problem is, the inherent, even if you make it conducting, you can never make as much conducting as you can make a silicon, because the electronic structure itself is different, which I'm not getting into details. More than that, the other problem with the organics is uh, the binding energy, what we call them as an exciton binding energy, is very high in organics. It means that in the case of organics, in the case of inorganics, when you generate electron and hole pair, I never said that you need some, they're always free, they can go, because of the binding energy is not high. But in the case of these organics, the exciton binding energy is so strong, they always want to stay together. Unless until you give them additional boost, they won't separate. So this is exactly what happens in the organic solar cells. What will happen is, you take a polymer, which is a donor, which gives electrons and holes, and then you have an acceptor, which will accept the whole electrons from the polymer, and then you will have this exciton generation, the diffusion, the charge collection, I mean the dissociation and the charge collection. These four things happens. And you don't have to worry about all these things, because it might be a bit too much for you to understand at this point of time. But all I wanted to say is that you do all fundamental aspects to get up to a level where you will be able to fabricate devices with some efficiencies, like that's what you're saying. There you're talking about 15, 20, 30, 40% kind of efficiencies. Here we are talking about 4%, 5%, because they are not still as good as that. But of course, there are papers where people have, I mean, this of course is my work, but there are people who have reported around 10, 12%. But these are the different things, because we wanted to use materials which are very cheap. And I didn't mention it. Probably I would say this is one of the cheapest solar cell that one could think of fabricating, because it doesn't use any expensive materials. But of course, the efficiency is low. So now people are interested to use materials which are cheap and make them more efficient. So and it involves a lot of fundamental understanding, and the nanoscience would come into the picture, how the donor and acceptor interface is important, and all the crystalline, how crystalline is this. So we do variety of characterizations and other techniques to say that this is good and this is how one should learn, one should look into these things. So with this, I will conclude saying that there is a lot of scope for improvement in this area, where one could use the least expensive materials and make them more efficient by using very fundamental science. And I always, recommend people that whatever you're learning in your +1, +2, in your engineering days, are the one which serves as a basics when you really want to do research, or the device that you're seeing in the outside world are the resultants of the fundamental understanding of these systems. Yeah. With this, I really thank the organizers for giving me this opportunity, and I'll be happy to take if you have any questions. Hello? Am I? Hello? Please someone respond, because I don't know whether you guys are around or not.
Thank you very much, Ramakrishna sir. So you have one query in the chat box. You can answer that.
Yeah, how quantum dots used to create intermediate band. So this is precisely what I told. The quantum dots are the one which are having a specific number of orbit. I mean, if you take any quantum dot, you're talking about 5, 6 nanometers or 10 nanometers kind of a systems. So when you have talking about 10 nanometers, you're talking about around 40, 50 atoms. So it means because of that, you have this intermediate, because of this bonding, anti-bonding orbitals, you will have these intermediate levels, which are not really close to atoms or not to the solid. Because of that, you will have this its own band structure. Yeah.
Dear participants, if you have any queries, you can put them in the chat box. Sir will take up the questions. I think a query from Dr. Joseph.
Yeah, because of all the technological developments in photovoltaics, as Einstein's 1905 theory of the photon undergone any changes? I mean, these are all the implications of that. I mean, when we know that a photoelectric effect means when you can generate, or you can generate the charge carriers from when shining the light. Using that concept, we could fabricate all these devices. So I really don't know what changes you are talking about. So yeah. I mean, the fundamental things have remained the same. I mean, that not only has helped in doing this, but many of those fundamental techniques like XPS, UPS are also based on this photoelectric effect, where you could characterize the materials by the kind of electrons that which are coming up, and those energy levels one could identify on that you can characterize your material itself. So yeah. I mean, it has got a lot of implications from fundamental understanding to basic characterizations to applications.
Okay, sir.
I think so. That's what my knowledge is, but I don't want to comment as such if there are any exceptions without me knowing it. So because that's not the kind of work that we do here. So to my knowledge, it still holds good. But if there are any exceptions to this or something else, I don't know. I mean, if there, but most likely it still holds good. Most likely. Thank you. Thank you so much.
Thank you, sir. Dear Ramakrishna sir, you have nicely explained the importance of intensity of sunlight in the fabrication of solar cells. Through simple discussion of atomic structure, you took us into the domains of nano and semiconductor world. The whole world is now talking about solar energy, of course, as alternate energy source. Dr. Ramakrishna sir had given an insight into this. Thank you very much, sir, for illuminating our participants about the solar cells. I now request Professor Rangappa sir to render the vote of thanks. We will be sharing the feedback link after this talk. So participants, please bear with us. So we'll be sharing in the chat box. So those who give the feedback will be getting their certificates. Thank you. Over to you, sir.
Thank you, madam. Good afternoon to everyone. Myself, Professor Rangappa, is very happy to deliver the vote of thanks. The management of Rajya Vakkaligar Sangha has always encouraged us to conduct various events to help student community and teaching fraternity. So I wholeheartedly thank for Sangha and the management. Dr. Ashwath MU, Principal BIT, has been supportive as ever in organizing and conducting events of this kind. I sincerely thank him on behalf of the Department of Physics BIT. I thank the speakers of the webinar, Dr. Sp Basuraju, former HOD, Department of Physics, BIT, for enlightening us on the history of photoelectric effect, and HSS Ramakrishna Mate, scientist ENS, for his wonderful talk on new generation solar cells. I am pleased to thank all faculty members from various colleges, teaching and non-teaching staff of all the departments of BIT, and beloved students for making this program a great success. Also, I thank the technician Vinay from Telecom Department. Also, I thank MBA HOD for having made us the special arrangement. I thank Dr. Nagaraj, HOD of Physics, Dr. GK Narsimurthy, convener of the webinar, and UP Raghavendra, Chelvaraju, Geetanjali, and Arshita madam for their valuable support. Thank you, thanking you one and all.
Thank you very much, dear participants, for your active involvement. We expect the same support in the upcoming events also. So we will be sharing the feedback link in the chat box. So you can give the feedback. Thank you, Ramakrishna sir. Thank you, SPB sir. Participants, you can click the link now. Okay, feedback link has been shared. You can give the valuable feedback. So thank you very much. That brings us to the end of the event. Thank you one and all once again.
The link now.